Let's take a look at the differential amplifier, and let's look at the DC analysis. So here's a differential amplifier circuit. It's a split supply circuit. I got a plus 15 up over here, I've got a minus 15 over here, and you've got the differential pair. Now, when you apply a signal to a differential amplifier, that normal input signals, they're centered around 0 volts DC. So what that means is you're applying an AC signal to a differential amplifier, and you're applying that AC signal to one input to the base of one transistor through a capacitor. So you take an AC signal and you apply it to that transistor there. And when we say it's centered around 0, what we're saying is that the signal itself is basically plus or minus voltage with the center point at 0. So if I want to do the DC analysis, what I want to do is take all the AC voltages to 0, and when I do that, what happens is I'm setting the input to 0 volts by grounding both inputs. So I apply a 0 volt input by basically shorting the base of both transistors to ground. Now, even though this is a ground point, I've tied this transistor here to ground, this is not the lowest voltage in the circuit. The lowest voltage in the circuit is over here. It's minus 15 volts. So if I connect this transistor to ground, current will not flow into that ground point. It'll actually flow out of that ground point this way to the minus 15 volts. And when it does that, it'll travel through the base emitter diode here. And so there will be a 0.7 volt drop across that diode. What that means is that the base voltage of both transistors, although the base voltage of both transistors is 0 volts, the emitter voltage of both of them is sitting at minus 0.7. So this point here is actually sitting at minus 0.7 volts. See, there's ground, current flows that way. The ground is at a higher potential than the emitters, so the emitters must be at minus 0.7. Knowing the voltage on the emitter, we can figure out what the voltage across this resistor here is, RE. I've got minus 0.7 at one end, and I've got minus 15 down at the other end, so there is 14.3 volts placed across that resistor. Now I can figure out the current that's going through that resistor. I can figure out IRE. I can take the 14.3 volts and I divide it by the 7 k ohm value of RE, and I come up with about 2 milliamps of current going through that transistor. Now, the next question is, if I have 2 milliamps of current flowing down here, how do you think that would split up? I've got the input to both of these transistors grounded to 0 volts, and both of these transistors are made on the same piece of silicone with the same characteristics. They're as close that two transistors can be so far as their characteristics are concerned. So if I have 2 milliamps down here and both of the inputs are shorted to ground, how do you think the current splits up between these two transistors? You might want to say, geez, Mr. Nelson, does it split it in two? And if you said that, you would be correct. Essentially what happens is we get half of the current coming down here, going through this transistor here, and we get the other half of the current coming down here. That creates a voltage across RC, which is the 5 k ohm resistor. Well, how much would that be? IC is 1 milliamps times an RC of 5K. So there should be a 5 volt drop across each of these resistors. And now we can figure out the voltage across the transistor. If this is 15 volts up here, if I lose 5 here, that means that this point right here normally sits at 10 volts. That's the DC operating point of the collectors, is they normally sit at 10 volts. And we've already said that the emitter sits at minus 0.7 volts. So the voltage across the transistor would be the collector voltage minus the emitter voltage, which would be VC minus VE, which is 10 volts, subtract minus 0.7. So there is 10.7 volts across that transistor, and there is 1 milliamp going through it. So your Q point would be 10.7 volts, 1 milliamp. That is your DC bias point. Okay, let's take a look at the AC analysis of the differential amplifier. And the process for doing the differential amplifier is the same as it is for any other amplifier. First thing you want to do is calculate R prime E, and you do that using the DC emitter current. And then you want to draw the AC equivalent circuit. I'm going to show you how to do that here. But the process is the same. You basically take part by part, you transfer it over here, and you connect it to things that it would be connected to in the AC circuit. Once we've drawn the AC equivalent circuit, we use Theveninizing and our equation writing to figure out what Z in and Z out and AV is from the AC equivalent circuit. And then the final step would be to redraw it as a two-port voltage model. So first off, R prime E. If you remember from the previous slide, we had about 1 milliamp of emitter current. So R prime E is going to be 25 millivolts over 1 milliamp. So it's going to be about 25 ohms. Let's draw the AC equivalent circuit. So the first thing that you see is that both of these transistors, right now they're connected to ground, but in use, they would actually be connected to some kind of an input signal through a transistor. So let's draw that. That input signal is an AC signal, so it will appear in the AC equivalent circuit like so. And you can note that we will apply that signal directly to the input of the first transistor, let's say over here. So we can put a box down for the transistor, like we do with the other circuits. And I'm going to just hold on before I put stuff in the box. I'm going to figure out the rest of it. So this is the base, this is the collector, and this is the emitter. Now looking out the collector of the transistor, we have one resistor, RC, which is a 5 kilo ohm resistor connected to one end of the collector, and at the other end it's connected to the 15 volt supply. The 15 volt supply will become an AC ground point in the AC equivalent circuit. So let's put that resistor over here. That's a 5K. That's our IC. This point here, this is where we would take an output from the differential amplifier. That would be like V out 1. Okay, so that's taking care of that resistor. Let's go this way now, and let's take a look at this line. We can see that the emitter of this transistor gets connected to the emitter of the next transistor. So we can do that over here. Let's put another box down for the other transistor. We'll call this one Q1. This one will be Q2. And we can connect these two guys by their emitters with a piece of wire. And then on that piece of wire, so that's this one here, on that piece of wire you can see in the middle it has an emitter resistor RE, which goes to the negative supply, but in the AC equivalent circuit the negative supply is an AC ground point. So we can draw that guy in here. That is RE, that is 7K, and this one was RC. And then we go to the second transistor, so there's E. If we look at the base of the second transistor, the base is connected to ground. There's that guy's base goes to ground. And then out his collector, I can see a 5K ohm resistor, which also goes to ground. So there's V out 1, and here's V out 2. So there's a second output voltage here, V out 2. There's our AC equivalent circuit. All we have to do now is put in our appropriate model that we want to use to analyze this, and we're going to put in the T model. So there's R prime E, that's 25 ohms. And there's our current source. So piece by piece, you basically transfer this over to the AC equivalent circuit, but in this particular one, there's two transistors. So you draw them as two transistors. If the input is applied over here to this transistor, then we'd say that that is our input. And then the emitters are joined together, our E goes to ground. There's your AC equivalent circuit. In our next slide, we're going to figure out how to extract Z in, Z out, and AV from that circuit. Finding Z-in of the differential amplifier is done using the same method that we did for all the other amplifiers. Basically what you do is you look into the input, and by Thevenizing you reduce all the impedances that you see down to a single impedance. So here we are, we got the AC equivalent circuit of the differential amplifier that we drew in the previous slide. The only thing I see is missing on this is we don't have the beta for the transistors. So let's use beta of 100 just to keep the math simple. Okay, so in order to Thevenize, what you do is you pretend that you are the source and you are the device putting a signal into the amplifier, and you need to figure out what all the impedances are looking into the input and reduce those to a single impedance. So if I put a signal generator here, I put a little signal on there, where would the current from that generator go? I can see it would go here, a little bit of it would go this way, down to that resistor, and then this is also a path to ground through this second R'(E). The current sources, when we're doing AC, we think of them as open circuits, so that path is blocked. So these are the paths to ground. There's RE and there's a couple R'(Es). In order to figure out the Thevenin equivalent in DC, sometimes you would start at the very far end. So we'll start here, and if we look this way, I would say the impedance to ground is a piece of wire, so that's 0. And when I come across the beta line, I would divide it by 100. Well, 0 divided by 100 is still 0, and then I get R'(E). So the impedance looking that way is basically R'(E) shorted to ground. So that's 25 ohms. Then I come back. Now if I look from this point here, what I'll see from that point is I will see RE in parallel with R'(E). So those two impedances are in parallel. So let's start writing this down. So Zin equals, if I start at the far end, it's R'(E), and that's going to be in parallel with RE. And then I continue to go back, and I get to this point here, and it's the two in parallel, and then I have the second R'(E) in series. So it's R'(E) in series with those two in parallel. And then when I continue to move over to the base side, and now when I'm looking into the base of Q1, our imaginary beta line is there, so it will be beta times all of that. So let's put some numbers in on this. We said beta would be about 100 times R'(E), that's 25 plus 25 ohms. Both the R'(Z) are 25 in parallel with 7K. Okay, real quick. 25 ohms in parallel with 7K. How much is that? 25 ohms. So that basically simplifies down to approximately 25 ohms. And I think it's reasonable at this point to start using some of the approximations as long as we're using them with understanding. So this ends up being, and you can see it, if you follow this path here, we have 125 ohm, and that's 7K, so we'll ignore that. And that is in series with a second 25 ohm. The impedance basically looking down from this point is about 50 ohms. And then when we come across the beta line, and we're looking at it from the base side, we basically have 100 times 50, 5K ohms. That is Z. Finding Z out on the differential amplifier. Well, the first thing you need to do is figure out how many loads you have attached and how are they attached to the outputs on the differential amplifier. So the differential amplifier has two potential outputs. There's one here. There's one here. There's two ways that you could attach a load to this. You could attach a load between the collector and ground on one of the outputs. That would be a single-ended output. Or you could put a load across the two outputs and you could drive both ends of the load. That would be a double-ended output. So let's assume that we are going to go with a single-ended output. So we're going to attach a load resistor to one of the outputs of one of the transistors. In order to find Z out, we would stand at this point and we would look back into the output impedance. We would stand at this point and we would look back into the output of the amplifier and we would ask what impedance is driving us. So let's remember also that when we Thevenize current sources, they become an open. So when I stand here and I look back into the circuit, there's only one impedance, and that is RC. So with a single-ended load, the output impedance is RC. So single-ended Z out equals RC. And then on a two-port model, you would draw it like this, where you have Z out, in this particular case, 5K. So Z out equals RC, which is 5K. Now, if you attach a load to both outputs, if you use a double-ended output, then what you have essentially is you have the load is attached. There's the load resistor. You have the load attached between the two outputs. And you need to Thevenize in both directions on the load resistor and figure out how much impedance it's connected to on both sides. So you would look in this direction. The current source is an open. When you look in this direction, I see that the path to ground is a single 5K. And when I look in this direction, I see that the path to ground is a single 5K. Remember, this one's been moved up over there. So for a double-ended Z out, basically what you have your dependent voltage source, and then one end of the load, so here's your load resistor. On one end of the load you have a 5K ohm resistor, let's say that one, and then looking out the other end of the load, you also have a 5K ohm resistor. Those are in series, so if we reduce them down to a single resistance, it would be 10K. So for a double-ended Z out, that's equal to 2 times RC, which is 10K. And I've drawn it here as two separate resistors, but when I ask you to draw the final AC voltage model, you would draw that as a single resistor. So there's Z out. Okay, last step here, finding the voltage gain is done by writing the equations for V in and V out in terms of transistor currents and impedances in the circuit. So this is done exactly the same way as we did it before. We say that AV is V out over V in. It's the output voltage over the input voltage. And the first thing we want to do is identify those points. So let's say right here, that's V out. And over here, we'll make this circuit here where we apply, this is where we apply the input voltage. We'll mark that as V in. So for V out is here. Let's draw, or let's write a formula for V out in terms of transistor currents and resistors. So the current that goes through this resistor, this is the only resistor in that neighborhood, and the current that goes through that resistor would be IC. So V out would be IC RC. And then V in, let's see, here's V in. When I apply V in here, a little bit of the current goes this way, and it goes that way. A tiny little bit goes there, but that's 7,000, and that's 25 ohms, so we can ignore this. So I would say that V in is going to be, this is now the emitter current. The current coming out of this terminal is the emitter current. So it's IE times R prime E plus R prime E. So let's eliminate IC and IE by putting both of them in terms of beta. So for IC, I would say that that is beta IB, and IE, I would say is beta plus 1 IB. And we're going to multiply that by RC over 2 R prime E. Now beta over beta plus 1, it was 100. I think we said in the previous example, I think we said that we were going to make betas equal 100. So betas were going to be 100. Well, 100 over 101 is essentially 1. So let us ignore this here, or approximate it to 1, and IB over IB cancels out, leaving us with the gain, the single-ended gain of a differential amplifier is RC over R prime E. And what that means, so if I have a load, if I am attaching a load, right here, a load resistor, the voltage across the load will be this much bigger. This is the gain factor. Sorry, the voltage across RC, because this is the open circuit voltage. The voltage across the collector resistor will be this times the voltage across the collector resistor will be this many times bigger than what's coming in. That's single-ended. Now, if we do double-ended, effectively what I'm doing is in single-ended, I'm holding this at ground and I'm wiggling one side of the load. But in double-ended, I'm wiggling both sides of the load. So the voltage applied to the load is going to be twice as big. So this is the single-ended load, but AV double-ended is just going to be RC over R prime E.